In this video, we'll explore another one of the very basic surveying calculations in coordinate geometry, the distance intersect. So in such an example, given we know the coordinates of A, which is point number 14, and B, which is point number 16. We also know the observed or measured distances from A to C and from B to C. So this may be a surveying example where this would not be very common, but where two known points exist, but for whatever reason, perhaps an angle can't be turned to C, maybe it's obstructed, whatever the reason may be, but the distance from B to C and from A to C are known. Now, often in reality, this is much shorter distances, and a distance intersect may be used to compute coordinates of a point that cannot be observed from a traverse station or has poor GPS reception, and two reference points may be set, but much closer. The bearing intersect is similar, but this uses different math. Bearing uses the law of sines. In this exercise, we use the law of cosines, which is found in section 11.1 of the book. So I made this example on longer legs, but it may be that this remote point that can't be observed correctly or in accordance with the rest of the survey standards for the project, perhaps these reference points are set 1 foot, 2 foot, 3 foot in more or less perpendicular directions, and then those distances might be measured with plumb bobs and steel pocket tapes. But in this example, this is what it is. It would be the same process to determine the coordinates of the unknown point. So we start with feeding the law of cosines in, which says that b squared equals a squared plus, ac squared plus ab squared minus 2 times ac times AB times the cosine of A. Now notice the reason that we use the law of cosines in a distance intersect is that we have all of the variables in this equation except for the cosine of A. So B to C is 165.86, A to C is 212.833, and A to B is 280.130. All those, we square them in the line below, and then we wind up solving for the cosine of A is 0.8073. The arcsine therefore tells us that the angle at A, because we're solving, look here, for the cosine of A, so when we find the cosine of A, we take the arcsine of 0.8073 and we get 36.169 degrees, which converts in bearings minutes and seconds to 36 degrees, 10 minutes, 9 seconds. Now, taking that information, we now have, using A and B's coordinates, we can compute the azimuth and the distance of A to B. So now that we know that this azimuth is 52.1927 and that the angle at A is 36.1009, we can solve for this interior angle and find that 52.1927 plus 36.1009 comes out to an azimuth of 88.2936. So using the azimuth which we have just computed, using the azimuth of A and B and the computed angle at A, we have the azimuth now. We knew the distance the whole time. So it's a pretty simple process now to compute the latitude and departure of the line A to C. We have done this before. And that brings us to a latitude of 5.596 and a departure of 212.795. Now we always want to stop, make sure that this makes sense. So the azimuth is less than 90, but it's close, so we're going mostly due east. So the latitude, because we're north of due east, we're climbing, so our latitude is going to be a positive value, but slightly. And our departure is also going to be a positive value and almost the length of the line. Notice that it's 212.759, whereas the length of the line is only slightly longer at 212.833. So now that we have this information, we can take our known coordinates of A, add the latitude and departure of A to C, and this brings us coordinates of C at 462.201 and 986.388. Now, no computation in the surveying world is all that sound or complete until we check it. There are two ways to check a distance. Distance intersect, I take the easier way. The way that another way that could be employed would be to duplicate the same process and compute the angle at B, add 180 to this, to your forward azimuth A to B, and then that would be, what, 232, 1927, subtract the angle at B off of that. That'll give you the azimuth of C, or of B to C, and then you can duplicate the process. But if you're paying attention and understand basic algebra and coordinate geometry, you realize that there is an easier way. Rather than duplicate this process with the law of cosines and have all these numbers to add, we just want to make sure that the coordinates that we've derived of C satisfy our givens, which is that the known distance, the measured distance from B to C, is 165.86. Being that we have computed coordinates on C and B, we can do a simple adding and subtracting and find the latitude and departure, which is difference north and difference east of the line B to C. And then simply by the Pythagorean theorem, you square both of these numbers, take the square root of the result, and it's 165.806. So that is the nice big green check mark. It works. So 165.86 is the same as our given distance. So the process works, and we have determined correctly the coordinates of C, which was the assignment for this little exercise. I hope you found this useful. Bearing intersects, distance intersects, they're the two most simple or fundamental surveying computations to compute coordinates of unknown points after basic traversing and computing latitudes and departures of observed angles and distances. And it's not impossible, it's not rocket science. This is what your tablet or data collector or desktop computer does when you feed in surveying software. You know A and B are 14 and 16 in this instance, and you know the distances, and you'll need to solve for this. Now, there is another